Hello everyone. Today we're going to be talking about histogramming, specifically high-performance histograms as objects, and we'll be using Boost-histogram to do so. So let's get started. So a histogram is best described as an object. Over the next 20 or 30 minutes, everything I'll be doing will be trying to convince you of this fact. Hopefully at the end you will agree with me. Now what do we have now? The current status is that we have numpy.histogram, we have matplotlib's histogram, and these are just functions that take some data and then produce a set of bins and some edges as arrays. There's no object associated with the histogram itself. There's several problems with this. For one, the API changes if you go to ND or if you use the 1 or 2D shortcut versions. It's hard to plot the results of a histogram once you have it. It's hard to tie different things such as axis labels and things like that to your axes and deal with those as well. And there's also these things called generalized histograms. SciPy does have access to those. They're called bin statistics, and it's a completely different beast. It's not the same procedure, not quite the same API. And what about manipulating or filling a histogram after you've filled it for the first time? These sorts of situations are not handled very well by this this method of using an array to have a histogram. So what would this histogram object look like? Well, it would probably have an axis, looks something like this. This is a 1D histogram. You see that it has an axis, and here you'll see that what the axis does is it takes a data space, a data coordinates, and it converts it into some sort of integer bin coordinates, and it fills bins. Each bin gets filled with an accumulator. So this could be a simple integer, it could be a floating point number, it could be something more complex that does a mean or some others, what other statistic you're interested in. There's also another thing that you'll see here that you may not be familiar with, and that's these flow bins. And you'll see why those are useful in a minute, but for now they're just an extra bin on either side that takes anything that misses the histogram completely. Okay. If we go ahead and expand this to 2D, you'll see that we have just two of these axes. They're the same object, the same axes. We just now have a collection of two of them. We just expand our storage to be 2D, and we just have the more accumulators. And you'll see here, again, these overflow bins. You can turn on or off the overflow bins for each axis. There's different types of axes. You could have regular binning, you could have regular binning. In fact, an axis could even have a discrete, it could convert from a discrete space to a discrete space. So you could have categories or something like that, integer strings. Okay, so here's some of the ideas for axes. We have regular, which would be a set binning, variable, which lets you specify the bins, categories, etc. And you also have these accumulators I've mentioned. Okay, so let's take a look at Boost-histogram and see what it would look like in Boost-histogram. So here we create a histogram. We can provide one or more axes, and you can optionally choose a storage. And then you fill this object. You can fill it multiple times. You can fill it once. And then you have something that you can manipulate. You can also do, as you see over here, a conversion back to this traditional output of NumPy. This would be sort of the classic style histograms. But you really probably shouldn't be using this directly. I'm hopefully going to show you that it's actually really, really nice to have this histogram object to manipulate. So let's take a look at what manipulation might look like. We have here a comparison between a Boost-histogram plot. Remember, Boost-histogram itself does not plot. It's a histogram library. Histograms are not images. They are binnings, like I've been describing. So you'll see that you can just hand this to matplotlib. We're just doing the simplest possible plot. Please don't actually plot a histogram quite like this. But this is what it looks like. You have your axis centers. You hand it the histogram and dots. The same thing in NumPy is a bit more verbose. You'll see you can just convert to NumPy. But with the centers, you have to do that manual calculation. With a Boost-histogram object, it's just natural. You just have the axes centers. Axes know their centers. You can also compute the density very easily. Here's an example of computing the density. You have you can just take a product of the widths. That would give you some sort of a volume, in-dimensional volume, and then you divide the each bin by the total of the bins, and then this. And this works for any number of dimensions, a one-dimensional histogram or a 10-dimensional histogram. This will give you the density. Here's another example. It's probably the longest code snippet I'll be showing today. But it just shows you that doing something relatively complex, like doing a threaded fill, is actually not that hard. You just write out the operations in terms of the histogram itself. So we have a copy, we reset it to nothing, and then we fill it. We do this on each thread, and then we just sum them up with a plus at the end. And it's natural and it works. Of course, preferably don't do that. Just use threads equals 4 or 8 or whatever, and do it that way. You don't have to write this every time. But that just shows you how easy it is to manipulate. Okay, and then here you'll see that I have a histogram. This is just the definition, so you can sort of see how many bins I have. And this is what it looks like. I could just hand this to some sort of plotting function. I'm actually going to be using the same plotting function every time. And I could make a little plot like this. And now if I want to make a rebinning of the axes, let's say I want to have, because this is a very high density histogram, save time. It saves time to do a very high density and then rebin later if you really want something different. I can just do a rebinning. So here I just use the slices, and I'll be talking about this later, but you can apply an action to each item in the axes. So I'm applying the rebin action, and I'm rebinning it, and there you can see what it looks like with a much coarser binning. And then I can also use this same technique to do slices, just like you do in NumPy, but in Boost-histogram, you can do slices over bin indices or in your data coordinates. So in data coordinates, all I have to do is read the values off of this axis here. So I read the X, read the Y off, I put those in as .loc, and there we go. I was able to very quickly and very easily zoom in on just the Python head in the image here. Images are really just histograms. They're just 2D histograms. That's how a camera works. So slicing and a lot of other things are just very natural this way, and it keeps track of the axes, it keeps track of the data that you attach to the axis, like the titles there, all that just carried along. And Boost-histogram is fast, speaking most specifically for Boost-histogram in this one. But in Boost-histogram, you can take, for example, this thing in NumPy, you can take that, and this is a fairly well-optimized piece of NumPy that does a one-dimensional regular binned histogram, but you can still do it at roughly twice the speed. Or if you do it with threads and you have an 8-core machine like mine, it doesn't scale perfectly, but you can still get another 2 or 3x speed up, which is very, very nice. And then if you go to 2-dimensional regular binning, which is basically an image, it's one of the most common types of 2-dimensional histograms, one of the most common types of histograms, period, probably. You'll see that if I do that, this is not highly optimized in NumPy. It's just falling back to the much slower variable bins method, and Boost-histogram can really shine here. And Boost-histogram doesn't actually do any special optimizations here. This is all just the C++ code underneath, and it's just selecting the best way to run this. So if you have a 10-dimensional histogram, this is still performs very well. And so for Boost-histogram itself, it's really built on a firm foundation. We have built it on top of PyBind 11, which is one of the most popular C++ binding libraries. It's a fantastic library, highly recommend it. It's used for SciPy itself, as well as a lot of other things. And we also built it using the Boost libraries, which is the closest thing you can get to the standard library for C++. It's easily one of the most respected libraries out there for C++. So, to quote Herb Sutter poorly. And the Boost-histogram library itself was one that was designed by Hans Dembinski. It was accepted into Boost 1.70, so it's not going away. And it's been improved in every version since. And that's the core behind the Python Boost-histogram bindings. Now, Boost-histogram itself has some really nice features. We have a variety of these. Feel free to look at those, but most importantly for our purposes, it was designed with Python bindings in mind. It was designed to both optimize extremely well for a static situation as well as a dynamic Python situation. And it does a really great job of that. So, and also we have the Boost-histogram author working directly on the Boost-histogram bindings, which is fantastic. It's really helped shape the direction, as well as some of the features that have been added to Boost-histogram. The Python bindings got pushed back into the C++ bindings, C++ library as well, which is exciting. Okay, and so we'll be looking at some of these in terms of the Python bindings here in a moment. So the new bindings for Boost-histogram were proposed roughly at the time it was being accepted into the Boost libraries. And they're focused on 4 specific pillars, things that we believed were not available in any other Python library. First, design, and then flexibility, and then performance, and finally distribution. We did not think any other library in Python could supply all 4 of these things. And hopefully you'll agree with me in a few minutes. Okay. So we'll be looking through each of these areas. The first of them is design. So you've already seen a little example of the design. It's designed to really just work as naturally as possible in Python. It supports pickling. It even supports the Cloud Pickle library. You can copy, and it does an optimized copy. The pickles themselves are also optimized for both space and storage, space and performance. And it supports operators. If you want to scale a histogram, just multiply it by a number. If you want to add 2 histograms, that just works. In fact, recently, this even works even if you have growing categories, which I'll talk about in a minute, which is particularly exciting. It also supports the NEP13 ufuncs. And we also have a variety of advanced access to axes. So axes returns a tuple with all of the axes in it, but you can also apply any of the axes properties or methods to that tuple directly, and it'll operate on all of the axes at the same time. So it's a really natural way to work with axes. I think you'll really like it. Quick note here as well on the Python 2 support, because we really want Boost-histogram to work absolutely everywhere, and because this was it's designed to be general, but it is heavily focusing on being a core library for the Scikit-HEP ecosystem. It does support, sadly, Python 2 for now, but hopefully you'll forgive that. But it will drop support soon. So now we come to unified histogram indexing. This is quite exciting, I think. This is an invention of Boost-histogram that allows you to do a variety of different indexing operations very naturally into a histogram. And these indexers can be shared across libraries. So a different library can come up with a new one, or they can mix and match. Doesn't matter where you get it from. So it's really helpful for libraries building on top of Boost-histogram. Okay, so for the first one here, you'll see that we have either a start and a stop for a range, or we have a value. So if you want to select a value, just like in NumPy, but these actually can either be integers like NumPy, and like NumPy, they will do a normal bin indexing, or they can be callables. If they are callable, they will be given the access and then called, and then the result will be used in the full Boost-histogram C++ space. And if that's the case, that's from -1, which is the underflow bin, all the way up to n, which is the overflow bin. So if you do that, you can then write these indexers such as these down here for overflow and underflow. The bh.loc you've already seen, though you may not have known you can also add a shift value to that, but it just returns an object that's callable. And then len actually is a perfectly valid thing in the system. It's just, the len of an axis is defined, so you can actually just use len there, and that will take you up to the end, but not include the overflow bin in a start-stop range. So this final piece is the action. The action is either a reducer or a rebinner. If it's just an integer, such as NumPy, this will throw an error. The design was that anything that works in NumPy should either work the same in Boost-histogram, or it should throw an error, and vice versa for the other case. So you can't do a strided slice into a histogram. That would produce a weird result, so that's not allowed to throw an error. But you can put in one of these actions. So the 2 actions here that we provide a bh.rebin, and that will rebin a histogram. That's one of the rebinners. It's the only one that's available right now. And there's also a sum operation, and that will sum over all of the items or all of the selected items in that particular axis. It's really quite nice. This can be the Python sum, or you can call bh.sum. They're the same thing. Eventually, you can actually add any, at least certainly for the reducers, you could have any reducer you want. That will come at some point soon. So it's in the full spec. And then finally, you can add a dictionary here. And if you add a dictionary, that dictionary just is a dictionary of the axis number, and then you can provide slices or items, whatever you would put on the other side. This allows you in a 15 or 20 dimensional histogram to just provide an operation on 1 or 2 of the axes. It's mostly designed for code to use behind the scenes, but you can use it here if you want. But certainly some libraries are expected to use this for things that have really large numbers of axes. Okay, so there's a variety of different axis types. This is a very flexible library because there's a variety of different axes types that you can use. For example, you have the regular axis, that's evenly spaced bins. That's actually a much faster lookup. You have a variable axis. You've got integer. You can do categories. Categories can be any collection of integers, any collection of strings. You can even select growth equals true, and these axes will grow automatically if they see a value outside. Or you can use the flow bins, and you can turn those on or off. But these have either flow bins or growth. And there's also even a circular axis type, which wraps around. And it's just a very natural way to do circular histograms. So that's really nice. So now we come to transforms. So this is a particularly exciting way to take a regular axis, which has that fast order 1 lookup, and continue to keep that fast order 1 lookup, but still provide some sort of conversion to a non-regular space, as long as you know the functional way to convert in and out. So for example, one of the ones provided in Boost-histogram is the log axis. So this is a way to do a log axis, and it's just about as fast as a regular axis. It scales beautifully. It doesn't scale like a normal sorted lookup would. Here's how you would write your own. So remember behind the scenes, we have a C++ library powering this, but you can actually use Numba to write a C callback, and you can hand that directly to the library and it will use that. So you can write anything you would like in for your transforms. You can use Numba, or you can compile it yourself, or you can use Python or any other way to produce a C-types pointer, and you can pass that in. You can even do pure Python if you want. I'm not going to show the example of that because it is slower. It's no slower than if it wrote this in Python, but it's much slower than these. These are only something like 7% slower than compiling it completely yourself without this function pointer addition. So it's really, really nice. So up here you have an example of what it would look like. You have the plot with regular spacing and then one with log spacing, and you can see the difference in the points. There's also a variety of storages. There's 7 storages that come with Boost-histogram. You have a double storage, which is sort of your normal storage. It's quite fast, and it goes up to a very large number of integers. It also supports weights, so it's just the most flexible of the storages. But you also have an integer-based storage if you want to force integers. You have an atomic integer, which is it's not really for high-speed filling. It's better to split the histograms usually and fill them separately. But it does allow you to fill this from several threads, and it's thread safe, and you don't have to worry about this not filling correctly from several threads. So that's quite nice. You also have this rather unique unlimited storage. It's something that's special to Boost-histogram, C++, and it's been carried over into the Python. And it's got a no overflow guarantee, and it starts out with as small as it can, 8-bit integers, and then it grows depending on how large the contents are. So it just takes up as little space as possible. So that's quite nice as well. There's also accumulator-based storages. These accumulator-based storages allow you to do some very powerful things. The weight stores both a value and a variance, so it keeps track of an uncertainty value for you. That's extremely useful in physics, and it's also used in a few other places as well. It's something it's hard to do in NumPy. And then you have these things, these mean accumulators, which make what are commonly called profile histograms, which are a quite powerful way to track a mean value. So you can use a 1D mean histogram to approximate a 2D sum histogram, actually. So up here you'll see that we have very smart views into these. The accumulators, this will return these special ones will return accumulators, but if you get an array of these, those are actually an augmented NumPy array. They have some NEP13 support. They have property-based access into the structured array inside, even to computed columns that don't exist, and they work most places. So that's quite nice. Makes them relatively easy to work with. Performance, we've already mentioned this. Just to show you again, the performance here is quite good. We're about a factor of 2 or so faster than NumPy for highly optimized situation, and when NumPy is less optimized, we are something more like a factor of 10 faster, and then we can get an extra of 3 or so x out of multiple cores. Again, this doesn't scale. It's not a highly parallel problem when you're filling a histogram because you fill the same bins. So this is splitting it, filling them, and putting them back together, just like I showed you before. But still, for a decent size fill, you can get a nice speed up that way. So for the performance here, you also can do something special in Boost-histogram. And this is due to the fact that we're thinking of histograms as objects. That is, you can take axes and you can treat those axes as multiple histograms. So for example, you might have a axis saying true or false for valid data or bad data. And you could fill your histogram, make that an axis, and you can very easily select all the true. And then if you need to look at the bad data or you need to look at them together, that's incredibly trivial to do. This up here is actually a binary or Boolean axis. We'll be having an actual shortcut for that very soon. But you have that. You can also do this string category. Here I'm assuming that you have strings, but you could also use integers here for some sort of, say, run number or file number or something. And you can put those all together and then split them later after you do the fill. That means you loop through the fill one time. You fill one time, and then you can select later, just like you would do with a pandas data frame and group bys and things like that. It's a very powerful way of thinking, and I think you'll find it sort of transforms the way you structure your applications, the way you structure your analysis, similar to a way that pandas restructures your thinking with the group bys and making selections later. Now, distribution is something that was very important. We wanted to make sure that Boost-histogram was available absolutely everywhere without fail. It had to be easy to install, easy to build, easy to use. So to do that, we had a few things helping us. One, everything was header only. So we had all of the Boost dependencies header only. We had the PyBind 11 was header only. So you didn't have any sort of compiled library you had to ship along with it, which is really, really nice. You can just use Git submodules and you're done. Downside is that it was C++14, so we had to work a little bit to make this available in as many places as possible. So we came up with a specialized GCC Docker container to do the Mini Linux 1 builds. We also used Mini Linux 2010. I think we're one of the first libraries to be using Mini Linux 2010 builds when that came out. And then we also support everything else. Now recently, we switched over to CI build wheel, which has been fantastic. I've been watching that for a while, helping a little bit, and now I think it's ready for us, and we were able to move everything we already had, and some of the special edge cases we'd worked out, we were able to make those possible inside CI build wheel. A few things to note in this. Conda Forge has dropped their Python 2 support, so the old files are still available there for Mac and Linux, but if somebody really needs Conda in Python 2, you need to talk with us, and we could possibly re-enable that. But right now we're only on Conda Forge, and then we support pretty much everything. Now Windows for 2.7, this requires the standard workarounds. It is built with a newer version of Visual Studio, so you can do it, just probably better not to use Python 2 on Windows. Probably better not to use Python 2. This also uses a few other things, like it uses the PEP 518 build system. So if you have C++14, it should just build, even if you don't have a wheel. We try to provide wheels for everything that you need and binaries for everything you need, but if not, it should just build on the box. Alpine and all these other odd systems, it should just work because the compilers are new enough. Okay. You'll also find some extremely helpful documentation here. The Scikit-HEP developer pages were based heavily on the work from Boost-histogram, and they cover how you set up from scratch all of this sort of distribution setup in GitHub Actions. And there's also, if you look at the blog link there, you'll also see how to do all of this in Azure using some of the older technologies, and sort of a discussion of how this happens, because CI build wheel hides a little bit of that for you, which is nice. But if you're curious to know what happens behind the scenes, it was all gone through in this first link. Okay. There's also a variety of checks to make sure that this remains as useful as possible. So there's also a variety of checks in place to make sure that this works well. We're using pre-commit, which is fantastic. GitHub Actions we're completely GitHub Actions now. And we're using Black to do the formatting. Lots of the different pre-commit hooks are being used. We have some basic checking with MyPy that's going to be improving in the next few months, but we already have a little bit of basic checking there. And we're using Flake8 Bugbear is really excellent at finding some bugs and odd corner cases that might cause problems down the line. Check manifest is really nice to make sure that you don't have missing files near manifest. And we're using Clang format for our C++. So those are all tools I highly recommend. And you'll find descriptions of those in that Scikit-HEP developer page if you want to know how to set those things up. We have an extensive test suite with more than 500 tests, and we have a variety of other things. The technology that's been used here, both to set up the basics as well as to do the wheel building and things, is already being used across many different projects in Scikit-HEP being picked up from this. So Particle and iMinui and PyHF all have at least some aspect of them has been improved by this work. Also, we weekly check. We have a GitHub action that weekly checks all our dependencies, updates them, and makes sure that something in Boost or Boost-histogram doesn't break. So we're ahead of the game there if something does break. And we've been using setup tools SCM for the versioning, which is really nice. So let's step back a little bit and look at the Scikit-HEP ecosystem. Where are we going with this? If all you want is histogramming, this may not be of interest to you, but you might want to know about a few of the other things that are out here. So this is really just a part of this. We have Hist, which is a package being built on top of this, designed for analysts. It'll actually have things like plotting built in. Boost-histogram will not have any dependencies or plotting other than NumPy dependency. So it has more dependencies in plotting, and it's much quicker if you want to work on in a notebook or in a command line. And we have Aghast, which converts between different formats. It doesn't actually do any histogramming itself. We have Histoprint, brand new member of the Scikit-HEP libraries, and that does printing on a command line. So you can print up to 5 histograms at the same time, which is kind of quite neat. And then the HEP-specific parts are really put into MPL-HEP, which does plotting, and it knows how to do plots the way that we like them in HEP. And then we have a tutorial site which pulls all the different pieces and packages together and shows them working together. So let's just take a quick look at Hist. Hist is coming this summer. We have a Google Summer of Code student working on this. And it's a Python 3 library that does a variety of things in a more compact and quick way for a command line. If you think of Boost-histogram like NumPy, you should think of Hist like pandas. So, for example, one of the shortcuts that will be added to Hist as an experimental shortcut will be using the letter J after a number to convert between the bin space and data coordinates. So you could just say 0.7J, and that would be the location data coordinate of 0.7. And also just using strings directly instead of putting loc. And that way you don't ever have to type loc in parentheses on the command line or in your notebook when you're working. Then we also have some ideas with metadata. This will actually assign meanings to metadata like titles and names and units, things like that. And that will be useful for plotting libraries. We'll have some built-in plotting as well, similar to the way that Pandas provides these. And there's also we're free to add some dependencies. So here's a very early look at a plot from Hist, and this is a pull plot. So you can see that you were able to plot a histogram, a fit, and compare those with a pull plot in Hist. So just to summarize the various things that we've covered, we looked at design. We saw how Boost-histogram was designed. We looked at flexibility. We saw how many options that it had and how natural these were mapped to different concepts. And we looked at performance and saw that we have very decent performance, easy access to things like the cores on your computer. And we looked a little bit at distribution and how easy it is to get Boost-histogram wherever you are, as well as the various documentation things that have been provided to make it easy for you to do this on your own library as well. So Boost-histogram is easy to install. You can just pip install it or conda install it from Conda Forge. It is very easy to convert to NumPy. In fact, if you just want to switch to NumPy from NumPy to Boost-histogram, get the benefit of that speed, and ignore everything else I've talked about, you can do that. Obviously, I prefer you listen to the other things I said, but you can do that. You can just call bh.numpy.histogram or histogram1 2D or ND and just get the benefit of that performance. It's the same API. You can also have that return an object if you want by adding a keyword-only argument, or you can convert later down if you have histogram objects, you can convert them back to the regular NumPy. And there's lots of new exciting things coming along the line, like Hist. So a histogram is best described as an object. I'm hoping that you now agree with me. And Boost-histogram is a really good example of one. Thank you for your time. We'd like to acknowledge the National Science Foundation and their support for this project. And there are a list of links here that you will find useful, hopefully, at some point. Thank you very much. You're supposed to applaud now. Waiting for the applause.